So hello everyone, in this video I am going to discuss 4 methods. First is Euler's method, second one is Euler's modified method, third is Runge-Kutta method, and the last one is shooting method. So let's start with Euler's method first. So Euler's method is also called as Runge-Kutta method of first order. Runge-Kutta method of first order. So in this question, if in any question asked, there is asked that you have to solve it using Runge-Kutta method of first order, then you have to use Euler's method. So what we do in this method is, let's suppose consider an example, dy by dx equals to x plus y, and y of 0 is equals to, suppose 1. You have to calculate y of 1 equals to what, and suppose step size h equals to 0.02. So the recursion formula for this method is yn plus 1 equals to yn plus h times fxn comma yn. Here this fxn comma yn is equals to the right hand side, that is, for this problem it is equals to x plus y. So yn plus 1 equals to yn plus h into xn plus yn. So starting with x not equals to 0, because we have given y of 0 equals to 1, y of 0 equals to 1. Now adding step size to it, x equals to 0.02, x2 equals to 0.04, x3 equals to 0.06, x4 equals to 0.08, and x5 equals to 1. So for x1 corresponding to, we have y1 equals to, from this recurrence relation, y0 plus h into x0 plus y0. So if we plug x0 equals to 0 and y0 equals to 1, we get y1. Similarly, we can get y2 equals to y1 plus h into x1 plus y1, and so on. From here we can get y5 equals to y of 1. So next, let's see how we can apply Euler's method for second order ODEs. Let's suppose consider an example, d2y by dt2 equals to 2y plus t, and let's suppose y at 0 equals to 1, y at 1 equals to what we have to calculate, and step size equals to 0.02 again. So what we do in this problem is that we can assume dy by dt equals to z, and then this equation gets converted into dz by dt equals to 2y plus t. So now we have two equations. For this equation we have y at 0 equals to 0. For this problem we have two boundary condition required. Y dash 0 equals to, let's suppose it is also given 1. For this we have z of 0 equals to 1. So now you can solve easily using Euler's method for first order ODEs these two system of differential equations, and you can solve finally this equation. So now let's move on to the second method, that is Euler's modified method. This method is also known as Runge-Kutta method of second order. This method is also known as Runge-Kutta method of second order. The recurrence formula for this method is that yn plus 1 equals to yn plus h into f of xn comma yn. In this method what we do is that we calculate yn plus 1 again and again until we get more and more precise value. Yn plus 1 equals yn plus 1 prime equals to yn plus h into h by 2 into f of xn comma yn plus f of xn comma yn plus 1. What we do, we put yn plus 1 here. Similarly, yn plus 1 double prime equals to yn plus h over 2 f of xn comma yn plus f of xn comma yn plus 1 prime. So we put yn plus 1 prime here. We continue this process until we get yn plus 1 prime. Suppose if yn plus 1 prime has last decimals first 4 digits same to this yn plus 1 prime, then we stop there until we continue this process. So this method, that's it. Let's move on to the third method, that is Runge-Kutta method for fourth order. In this method, consider dy by dx equals to x plus y, and we have y of 0 equals to, suppose 1, y of 1 equals to what? It's equals to 0.02 again. So what we do in this question is we calculate lots of k's, that is k1 equals to h into f of xn comma yn, k2 equals to h into f of xn plus h over 2 comma yn plus k1 over 2. This k1 we put here. Similarly, k3 equals to h into f xn plus h over 2 comma yn plus k2 over 2. k4 equals to h into f xn plus h over 2 comma yn, in k4 we have xn plus h yn plus k3. Here we put h and k3. So from here we get k is equals to 1 by 6 k1 plus 2k2 plus 2k3 plus k4. See, here we have in denominator we have 2, so we multiply k2 and k3 by 2. So once we calculate k, we have the recurrence formula equals to yn plus 1 equals to yn plus k. Similarly, for n equals to so in this method what we do, first put n equals to 0. Let's consider this example. dy by dx equals to x plus y. Okay, and we have y of 0 equals to 1 and y of 1 we have to calculate, h equals to 0.02. So what we do, first for n equals to 0, we calculate k1 first from this formula. K1 equals to h into this, we calculate k2. Similarly we calculate k. Once we calculate k, we get y of, from this recurrence relation, y of 1 equals to y of 0 plus k. So for n equals to 0 we have done. Now proceed for n equals to 1. For n equals to 1 we have to again calculate k1, k2 and lot k's, and we get y2 equals to y1 plus k. Okay, so we have to continue this process until for 5 times because we have step size 0.02. That's it for this method. So let's see Runge-Kutta method for second order. ODEs. Let's consider an example that x double dot plus k by mx equals to 0. let's put k by m equals to 1 also. So x double dot equals to minus x. This is an equation of SHM. We have given x of 0 equals to 3 and x dot of 0 equals to 0. So what we have to do in this problem, it is similar to the Euler's method for second order ODEs. We have to split it into two system of first order ODEs. So let's assume x dot equals to v. This is my first equation. For this we have x of 0 equals to 3 and the second equation is x double dot, that is x double dot, that is equals to v dot equals to minus x. So let us consider this as f1 t comma x comma v, and this is f2 t comma x comma v. So what we have to do is that we have to calculate lots of ki's for this also. For x dot, for this equation we have to calculate k1x, k2x, k3x, k4x and finally k. So k1x equals to h into f ti comma xi comma vi. Similarly k2x equals to h into f of ti plus h over 2 xi plus k1x over 2 comma vi plus k1v over 2 vi plus k1v over 2. Similarly k3x equals to f into ti plus h over 2 comma xi plus k2x. Now we have to put k2x over 2. So it is similar to the RK4 method for first order ODE, that, and only difference is that we have to add this term extra. Similarly for k4x we don't have anything in denominator, and we have to calculate k like that 1 over 6 k1 plus k1x plus 2 k2x plus 2 k3x plus k4x. And for v dot we have to similarly, here we have to put f1. Okay, for v dot we have to do for everything for that f2, k2v, k3v, k4v and k. Okay, so you can put for this we have h into f2 ti comma xi comma vi like that. So once you calculate all the case, you can do xi plus 1 equals to xi plus k, and similarly vi plus 1 equals to vi plus, here we have kx, here we have kb. Okay, so this is the article second order ODEs. So now let's move on to the last part, that is suiting method. So suiting method is boundary value problem. Okay, like RK4 method and Euler method, this is all initial value problem, but this is boundary value problem. Let's consider an example, d2y by dx2 equals to 2y plus 3x. Okay, and we have y of 0 equals to 0, y of 9 equals to 15, and we have to calculate, and step size equals to suppose 3, and we have to calculate something y at 5 or whatever. Okay, so what we do in this question is we convert it into initial value problem. Like we assume y dash 0 equals to something, let's suppose k1. Okay, and we solve the problem like d2y by dx2 equals to 2y by 2y plus 3x, and we have y of 0 equals to 0 and y of 9 equals y dash of 0 equals to k1. So we can solve it and we can get y of 9 equals to what from here. Let's suppose we get q1. Okay, Then we again change our assumption. Let y dash of 0 equals to something k2, d2y by dx2 equals to 2y plus 3x, y of 0 equals to 0 and y dash of 0 equals to now k2. So this is again similar problem we have seen in RK4 method for second order ODs. So let's this time we get y of 9 equals to something q2. Okay, so now we have table. For k1 we get the y value q1 and for k2 we get q2. Now the k required, okay, what we have to assume is given by a formula. K equals to, the formula is k equals to k1 plus k1 minus k2 minus k1 upon k2 minus k1 upon q2 minus q1 into q minus q1. Okay, so here q is the required value, that is 15. Okay, so we have to plug it here, k1 k2 and k everything. We get the k required, that is y dash 0 equals to k required. So our final assumption is y dash 0 equals to k required. So d2y by dx2 equals to 2y plus 3x and y dash 0 equals to 0 and y dash 0 equals to k required. So from here we finally calculate y9.